I'm on page 53. Okay, so shown is a slow field for which of the following differential equations. I like to look for a number of things. I like to look for where do I see slope undefined. If I can match slope undefined with something that I know to be true or something I know to be false, I can eliminate wrong choices. Second big thing is looking for slope zeros. Looking for positive slopes or where positive slopes are located. And then finally, negative slopes. We have to kind of rely on these big picture because we don't know exactly what the steepness of every one of these points are. Now, one thing that does stand out here is notice that when x's and y's are the same values, we're getting all the same slopes, right? So that's something that sticks out a little bit. It looks like they all are looking like slope ones, and they're all the same slopes. So that means at y equals x, looks like my slope should all be around 1. And we know this can't be true here because xy minus 1. So if I chose 1, 1, I should be getting a positive slope. But if I plug 1, 1 in here, 1 times 1 is 1, 1 minus 1 is 0, and I don't see slope 0 here. So x plus y, if it's truly x plus y, then 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8. It should be getting steeper and steeper. It shouldn't be staying the same slope. So I know this can't be true. 1 minus x minus y. So if I plug in 1 to 1 here, I'll get minus 1, minus 1. So that's a negative slope. I don't see any negative slopes here. So just by looking at 1, 1, I'm able to see my choice here. If I have 1, 1 or 2, 2 or 3, 3 or 4, 4, all my x and y's cancel out. I'm always just be left with 1. And if you're absolutely stuck between two choices and you're trying to decide which one is which, then just pick an order pair like 1, 1 and say, okay, I don't know if that's 1, but I know it's positive. So I'm going to plug 1, 1 and I should get positive. And if I still can't get something to be different, then look at another order pair. Okay, pick another order pair. -3, 2. I should be getting a slightly gradual negative slope, right? Okay, so if worst comes to worst, you can always plug in order pairs and say, okay, I don't know what that exact slope is, but I know it's negative. Am I getting negative when I put it into the formula? Okay, 43. Differential equations. Hopefully, we've done enough of these where we feel comfortable with the process. You separate the variables. Isolate the left side as minimal as possible. And this ends up being power rule on the left. Once you expand, the right side is power rule on the right. Solve for C. Once you solve for C, then put it back into the equation, try to solve for Y. Now, if at the end you see that it ends up being a plus or minus square root, then make sure you choose your appropriate solution based off of your given order pair. If your given order pair has a Y value that's positive, you want to pick the positive square root. If your Y value at the end is negative Y value, then you want to choose a negative square root. here's something, I mean, it's not foolproof, but it is something nice to kind of give you some assurance at the very end. Is that when you're staring at your final equation and you just want to get extra assurance that your equation is correct, go ahead and plug in your order pair. It should work. Right? If your order pair doesn't work, that means, okay, that means something didn't go quite right. Either you didn't solve for the C correctly, or you didn't solve for the Y correctly. But in the end, if your order pair, if you can plug in a 1 and get a 4 in return, that's usually a pretty good indication that your answer is probably right. Or here's something else. If you're staring at your answer choices and you have no idea where to go ahead and plug in your order pair in each of these. Right? If an order pair doesn't work, then you know it can't be the right answer. So that's a clear indication as well. Yeah, that's almost like a cheat way of going through it. But if you look at C and D, you plug in 1 and 4, there's no way you're getting 4 with that E sitting there. So you know those are obviously incorrect choices. Andrew. So, okay. Thank you. Okay. Page 54, number 44. Here, you may be seeing some variables that you don't recognize, but just understand. If you don't see, if you see a variable that seems strange, that's your Y, okay? That's your Y variable. And then usually, if it's a strange variable, it's always paired with time. So T is your X, here P is your Y. So go ahead and set up in a way where you can get a fraction equaling a fraction. And then cross multiply. And then once you cross multiply, you can clearly see, okay, the 10 minus P needs to be with the dP. So I need to divide those sides by 10 minus P. Okay, go through your substitution. It ends up being a natural log on the left side. Plus C shows up, plug in your order pair. Well, in this case, I think I solved for P first. I solved for P first, then I plugged in my order pair. I always put the C on the right side. Yeah. You don't have to, but because we want the left side to eventually be just the P variable, anything that I can put on the right side, I want to put on the right side.
And C will always be positive, right? So even if I was to move it to like the,
That's right, that's right. Yeah, it's always gonna be a plus C, but in the end, your C value may be a negative value. And if that's the case, then you can replace the C with a negative number.
But when I'm like using just the.
Right, if it's just a notation, it's always just a plus C, yeah. And plus C just means it can represent any positive or negative integer, yeah. Yeah, typically, I mean, I'm hoping that students feel more comfortable with differential equations, but it's almost like, even though if you know how to do it, I don't know, I'm kind of um, mixed about what to do here, because it's like, okay, it's great that we can work through this problem, but is it coming at the risk of missing out on doing two other problems? You know, so it's like, we gotta, find that balance. It's like, this is not a hard problem, but it is, kind of time consuming, and you're spending potentially 4 or 5 minutes when you could be hitting other problems. So I don't know. I feel like, okay, it's like, okay, if you know how to do this, but it takes a long time, circle it, make sure there aren't other easy problems lying around, and then come back to this one to finish it. So, yeah, I just want to see what we can do to manage our 60 minutes efficiently, having to go through 30 of these problems. So. Okay, 45. Notice this is one of those problems where you may be solving the differential equation, which is all fine and good, but you almost want to pay attention to your answer choices, because your answer choices may not be solving it all the way. So it may be representing your answer in a form that is half complete. So whenever you do a multiple choice problem, always keep looking back at your answer choices and make sure that you haven't bypassed the solution. But here, once I get to this point, this interval notation, I'm already sitting at the right choice here. And this is representing something that is correct up to this point. And then if you plug in your ordered pair at this stage, it'll end up giving you the right answer. So that's kind of tricky here with part D. You almost have to test between C and D to see which one will match the better answer for you. And also between C and D, this is the only ordered pair that's going to work. Because if I plug in root pi in for my upper bound, my bounds will match. This will go away. And then I'm left with 4, which is the y value that I'm looking for. Meanwhile, if I plug in root pi in here, this is not going away. And this plus 4 is not the same thing as 4. Okay, these are cumulative review problems. These are not multiple choice, but still good to practice through. Whenever I see anything with the piecewise function and dimension continuity, I'm always stepping through continuity conditions. Kind of gives me a structure for me to kind of work through my problems. If I can step through continuity conditions, I should always be able to figure out, okay, is there, if there's a issue, I should be able to identify it a little bit easier within continuity conditions. But here, I can plug in 0, get a real number, get a 1, evaluate the one side limit, they match, I get 1 as well. First condition is 1, second condition is 1. So by continuity conditions, my function is continuous. Number 2 is also continuity conditions. but you have to find the limit of that expression. And if you don't remember the conjugate method, you could also go through L'Hopital's rule. If I plug 1 in, I get 4 minus 4, which is root 4 minus root 4, which is 0, 0 over 0. But I know I can, you don't want to go through the conjugate method. A little messy, but you can still go through L'Hopital's rule. So derivative of this, and the derivative of this. Okay, reevaluate, plug 1 into the remaining x's, see what happens. This is 2. Square root of 4 is 2, but I have to put that in the denominator, so 1/4. This is 2, the denominator, 1/4 times 3, 3/4. You can still get to the right answer with L'Hopital's rule. Okay, must be -1/2 because that's what the limit is, and that's what we're looking for.
So like problem is we don't even have to worry about where this is K, but that's.
Okay, so that's the first condition. First condition, we don't know what that value is. F of 1 equals K, right? We know the limit will produce -1/2. So the third condition will have to be where this is equal to that. And so that forces us to match K must be equal to -1/2.
Oh, so we're using the other.
Yeah, so we're using continuity conditions to step through, but to find the limit, you can either do this conjugate method with factoring, or you can go through L'Hopital's rule to get to the limit. Either way, you can get to the limit. But then the K value is moving to the third condition and see, okay, if my limit is -1/2, if my F of 1 equals K, then put two and two together, K must be equal to -1/2. Okay. Number 3, it's we have to really understand how to break this down. H of x equals g of f of x. This is not product rule. This is the function within a function. We got to go through chain rule. So spell out your chain rule. Outside derivative times inside derivative. So my outside function is g. So outside derivative is g prime of f of x. Inside derivative is f prime. So this is how I'm going to build my derivative. H prime equals g prime of f of x times f prime. First things first, replace every x you see with 2. And then work your way from the inside out. So f of 2 is the order pair. So f of 2 is 3. Replace f of 2 with 3, and then take a step back and say, okay, what's left over? I'm asking for, it's asking for g prime of 3 and f prime of 2. So f prime of 2, the slope of the f graph at 2, this is the slope of -1. And then look at the g graph, find the slope of the g graph at 3. This is this line segment. If I pick 2 points, that lands at a nice point I can identify. The slope is up 2 over 3, 2/3. 2/3 times -1, -2/3.
So if it's asking for just geometric effects, we find the point.
That's
If
right.
it's asking for the prime, we find the slope.
Well, good.
What if it asks for double?
This double prime then is asking for the concavity. And usually, I would say you're not gonna see that happen unless they give you the F prime and G prime. Right,
So if they give you the F prime, G prime.
then it's the slope.
Okay.
Right, so typically, on the graph, they're not asking for the concavity. Yeah, I would say that's not. Yeah, I can see that. A56, recognize this as the need for quotient rule. F prime G minus F G prime all over G squared. K of X, you have to leave it in function notation. 3x, we can actually go through power rule to get the derivative. And then after you build your derivative, then you're just pulling values from the table, get down to the numeric answer. Okay, number 5. Whenever you see that squared or cubed or fourth with a trig function, take the time to rewrite it because it's going to be a lot easier seeing the need for chain rule if you put that 2 outside a set of brackets. If you see it outside a set of brackets, you can see, okay, I got to take care of the bracket first, then the tangent, and then the parentheses. Right, so 2 bracket to the first power, tangent becomes secant squared of u, and then finally u prime. And make sure that you don't put each of the derivatives within each other, that you put them apart from each other. They're all claiming their own space.
The difference between what was originally written and
They're the same thing, but it's harder to see the need for chain rule here. It's easier to see the chain rule need here. Because if you don't pull that 2 out, you're going to forget that, oh, I got to worry about tangent 3x squared. A lot of students, they will just say, oh, 2 tangent, and they'll just do 3x squared becomes 6x. They forget to take care of the fact that tangent will turn into a secant squared. Okay, you got problems. Problem here that is going back to that relationship between a function and its inverse. So I want to find the derivative of inverse of p at 5. So I know that 5 is the x value of my inverse, but it must be the y value of my original function. So I'm going to put 5 into the y value of my p of x. I'm just going, in this case, I can solve by hand. Cube both sides, add 1, divide by 2, I get 63. So I know my order pair is 63. If I can find p prime of 63, then that slope will lead me to the slope I'm looking for. So to find p prime, I got to go through chain rule. Outside's derivative times inside's derivative. Plug in 63. Get 2 over 75. as your P prime of 63. So therefore, the inverse at its corresponding point must be 75/2. Just the reciprocal, don't change the signs. So 2 times 63 is 126. 126 minus 1 is 125. Cube root of 125 is 5. 5 squared is 25. That's where that 25 came from.
Is that a higher?
That's an n. Yeah, I just gave some unknown value, whatever value I find, I'm gonna make sure I flip it. Okay, number 7, you have to find the second derivative. But to get to the first derivative, I know I see a need for implicit because I see something strange done with the y. So every time I find y's derivative, I need to attach dy dx. Once I find dy dx, then I gotta figure out, okay, how can I make my way to another derivative from here? So I'm gonna bring that y up to the top, get it ready for power rule again. Go through power rule, but I'm asking for y's derivative, so another dy dx will pop up. Place dy dx with what you found initially. And once you make that substitution, then you have your second derivative clearly in terms of just x and y. You try to clean up to your answer. Okay, questions? Okay. You guys okay? All right, 57. Okay, now you guys saw something like this on the quiz. Right, where you're gonna have to set the equations equal to each other and set the derivatives equal to each other. So don't let k and b throw you off. Treat it like you would if it was a number. And for which of the following values of k and b will the function be both continuous and differentiable? So continuous means that these two equations, they must meet at 1 with the same y value. And also, differentiable means that not only are they going to meet with the same y value, they're going to meet at 1 with the same slope. So the fact that they share the same y value means we can set the equations equal to each other. The fact that they share the same slope means we can set their derivatives equal to each other. So the derivative of x squared plus kx minus 3 is 2x plus k. Remember, k is just a number. If it was 3x, you would just say 3. If it was kx, you would say k. Right? So that's why kx becomes k. 3x plus b, imagine this is 3x plus 8. The 8 will go away to a 0. Same thing with the b. B will go away to a 0. So you set each of their derivatives equal to each other. That will allow you to solve for k, and then plug into one of the other equations, solve for b, Number 9, find the fifth derivative. Sounds daunting, but we just have to kind of follow the pattern here. So remember, k is just a number. So imagine, how would you handle this problem if it was e to the 3x? If e to the 3x, you just say 3 e to the 3x times 3. Same thing here. Y prime equals e to the kx times k. If you find the second derivative, that e to the kx will produce another k. And the k in front is just a number. So there's no need for product rule. It's just continually adds more and more k's. Just like if it was like 2e to, e to the 2x, every time you find the derivative, another 2 will pop up. They can multiply in front. And once you get to the fifth derivative, there's going to be 5k sitting out here. So k to the fifth, e to the kx. Number 10. Where is f prime is 0 equal to 3? They're mentioning the derivative, so you got to get to the derivative. To get to the derivative, you have to go through quotient rule. Sorry, no problem. So quotient rule, f prime g minus f g prime. Again, I know we get a little nervous when we see something that we don't recognize, that a is sitting there. Just pretend that a is a number and just treat it the same way that you would any other number. But in the end, we got to hold on to that a value, replace every x with 0, and then cross multiply and just see if you can figure out a way to get that a by itself. And there's two solutions for a equals 0 or a equals 2. Okay, I'll pick up the rest in class and also at this afternoon. Okay.